For the test on Thursday,
Uh-huh.
will we do what we did last week, like just join like an hour later for class?
According to the schedule, I have no presentation to make on that day.
Oh, okay.
Right. So if you show up in person, you can take the entire time to do the exam. If you do it online, of course, there's no limit.
It's just due before midnight, right?
Yes. Yes. In fact, next Thursday, if you show up in person, I may not be here right at 9 o'clock. My wife's got a medical procedure that may run long. So what I'll do is I'll leave hard copies in a folder on the computer table over here, out of the way, so prying eyes won't see it. And you can just come in the room, make a copy, and do your exam and leave it there when you're done. But I should be. Yep.
Is that like Thursday, like 2 days from now, Thursday?
Yes.
Right. Okay, I thought so.
Yeah. I expect I'll be in probably by 9:30 at the latest. So if you get started, I'll probably be here before you finish. And if you, what I'll do is when I come in, I'll open up the Zoom session until 11 o'clock. So if you decide to take the test online, then I'll be here. Well, that doesn't help much because you're going to be locked into a lockdown browser, so you won't be able to Zoom. But if you're having trouble, text me on my phone, and I'll see if I can fix it.
And is there a sheet you said to print off for Thursday?
A sheet to print off for Thursday?
Yeah, is that what you said?
Well, there are review documents. Do you have a copy of those yet?
No.
That's what we're going to use. We're going to use this one today to review for the exam. It looks like this. In fact, it looks exactly like a paper exam.
Mm-hmm.
My review documents are structured that way so that you can use them to practice taking an exam with this thing. And then, of course, the work problems are here in handwritten version. But both of these documents are in Brightspace in the course.
Okay.
They'll be in module 2 for this exam.
And then all formulas we just remember for the test, right?
No, actually. Here, on the back pages of the paper exam, you'll find useful information. Right, so you have all that information there. You have polyatomic ions, and you have a periodic table. And if you take the exam online, there will be a separate document in that same module with the exam. And what you need to do is before you start the exam, print those documents off. So you'll have them there in front of you. Because once you get in a lockdown browser, is going to prevent you from doing anything but the exam.
Okay, because that's what I messed up on, I think, on the last test, not printing it before.
Yeah. There wasn't a whole lot of information except for maybe the periodic table in the first exam. In fact, I don't even think it was there. No, because we hadn't gotten into the periodic table yet. But it would be wise to print this off before this exam.
Okay.
Let's see.
And do we just show that paper to the Zoom camera before we take the test and be like, this is the provided material, so they don't think we have like anything else?
Can, but I'll know it.
Okay.
The Respondus has you go through a startup procedure where you show your ID and scan the room and all that stuff. And that's really all you have to do.
Okay.
Let's see. Well, I better take roll. Let's see. So we're going to start off. The review document in this case is divided into two sections. Chapter 4 first, and then chapter 5. But the numbers are in sequence. So when you get to the end of chapter 4 review, you just continue with the same numbering. So I won't have to identify that when I talk about them up here. We're going to do the whole first page. Later on, we start getting to we have redundant questions, repetitive exercises, and then I'll start skipping. But in the beginning, this is new stuff. All right, number 1. The symbol for the element iodine. So we're into memory region. Have you memorized all the symbols that I identified in this periodic table? This one right here, with the red boxes and the blue background for the diatomics. All right, what's iodine? Right. Iodine's one of the simpler ones, and one of the logical ones is just I. That's iodine. That marker's about to kick the bucket. How about the symbol for lead? Now we're getting into more cryptic territory. Lead is one of those that's based upon the Latin. Right? PB for plumbum. And like any of the other symbols that have 2 letters in their ID, the first one's capitalized, the second one's small. If you put 2 capitals in there, it's wrong. No matter what the letters are, they're both capital and the symbol is wrong. All right, let's see. 3.
Now there's 3. Are both the second and the third lowercase, or are they? For like the ones on the very end, it's like normally it's like UUB or like UUV of the periodic table.
Oh. It depends on what version of the table you have.
Okay.
Down these the heavier elements down here, right in here.
Mm-hmm.
Some periodic tables, and it may be the one. I think, yeah, you are looking at that one. No, that one's okay. If you happen to see 3 letters, those are placeholders. So, for instance, if we had, let's see, the heaviest element in the periodic table is atomic number 118.
Mm-hmm.
It has 118 protons. Before it got a name, the IUPAC devised this scheme for a placeholding name. And they based it upon I think it was the Latin, actually. The Latin equivalent for each of these numbers in sequence. So this one would be on, and then this one would be on for 1-1, and this one would be octium for 8. And then they put an IUM on the end. So that's octium or UUO. Okay? So when you see in any periodic tables, the older versions, if you see 3 letters, those are placeholders.
Okay, so those have been named now, like they're the same thing.
I'm sorry?
Now these ones have been named.
Yes, yes, they all have names now. This particular one is OG. They stump the band. I'm trying to remember what that stands for. I don't remember. OG. I don't have it handy. But you're not going to be responsible for any of those. Any of those that were three-letter placeholders at one time now have true names and symbols. You won't be responsible for those. I didn't mark off any of those for memory in the periodic table. Okay, how about 3? Which of the following elements is an alkali metal? Okay, so you got to remember your group names. Some of the groups in the periodic table have names. And alkali metals are the ones farthest to the left, right? The first column. So you just take your periodic table and see which one of these match. As it turns out, sodium is the only one in there that is an alkali metal. About 4, an atom with 45 protons. Right? If it has 45 protons and has a mass number of 100, it must have how many neutrons? Okay. They don't even ask us what it is. You don't need to know that to answer the question. You just need to know the definition of atomic number and mass number, how they're put together, right? This number is equal to the number of protons plus the number of neutrons. Okay, so if we know the protons are 45, then the number of neutrons have to be 100 minus 45, which would be 55, correct? So that's why the answer is A. Okay, let's see. I better scroll. I think I chopped off the bottom of this one. Yep. Number 5. What's the most abundant element in the human body? Okay, think about what things are made of. What's the most common element in the human body? Water. Humans are often referred to in science fiction literature anyway as water bags. We're mostly water. And actually, this question could be a little clearer. Are we talking about by numbers of molecules, numbers of atoms, or are we talking about mass? And they usually mean mass in this context. So by mass, oxygen is the most abundant element in the human body. Water, yes, but there are other molecules in the body that contribute to the amount of oxygen. So oxygen is the most abundant due to water. And what else do we have? Well, I'll give you a little biochemistry lesson. We've got carbohydrates. Right. Like starches and sugars. And then we have proteins. They all have substantial amounts of oxygen in them. And then we have nucleic acids. Right? Everybody's heard of DNA and RNA. They all have large amounts of oxygen in them. So that explains why the most abundant element is oxygen.
Is Thursday the same day that those worksheets are due?
Yes, right. Those extra credits. Yeah.
Oh, are they extra
Some
credit?
that- Yeah, they're extra credit. Where you fill in the periodic table
Uh-huh.
and you name compounds.
Uh-huh.
I think there are 50 of them. You either write the name for the compound or you write the compound for the name. Yeah, those are extra credit.
Oh, okay.
I've got 3. One person turned in both of them already online, and maybe 3 other people turned in one of the, like, naming the compounds. So I'm starting to collect some already.
Now, if I like print it out and I take a picture of it, is there any way I could email that one to you?
Well, there's a place for you to submit it in Brightspace.
Can I upload just a regular image in there? Because I tried downloading it to a Word document, but it didn't work right. For the periodic table one, not the naming one. That one I can do on the document.
It should be in a PDF form.
Because when I like try to like open it, it says I can't like edit it. So when I try to copy and paste it, it doesn't actually paste the table. It just pastes all the, like, it didn't paste anything. It says like I can't copy an image.
You should be able to download the PDF file and then print it. Have you tried that?
Yeah, that's what I end up doing. I ended up printing it. So now I just have it like in paper.
Yeah. Well, for the periodic table, that's the only way to do it.
Okay.
Well, I take that back. I have some students that have managed to fill it in with editor of some kind, but I don't know how they do it.
Yeah, I tried, but then I got frustrated, so I stopped.
It's meant to be done by hand, and then you take
Okay.
a picture of the image that you create. And if you wouldn't mind, take a picture of the front sheet also, because I use that for grading.
Okay.
And include both of them. Let's see. 5. Where are we headed? That's the first page. Now we're going to skip down to number 7. Let's see. I'll have to scroll that. How about the symbol for copper? I'll give you a hint. It's not CO. CO is cobalt. So copper is Cu, based on the Latin cuprum. How about let's skip down to 10. Now, at any time, if you want to stop at any of these that I skip, just holler, call out, and say, I want to look at a different one. In fact, we can look at anything you want to. If it just suddenly occurs to you that you had trouble with one, well, let's deal with it. Otherwise, I'll just keep going through the ones I picked out. An atom that has 54 protons, number 10. Okay, so we have 54 protons there, 54 electrons, and 78 neutrons. Okay. What do you need to know? Do we have information here to answer that question? Yeah. All you need to know is the number of protons. And you can go straight to your periodic table and look for 54 protons, and just follow along until you find one that matches. In fact, I've already got the X. I'll just add the E. That's a xenon. It's a noble gas. We can also tell from this information, it's not part of the question, but this is a neutral atom. It's got the same number of protons as electrons. We can also say something about the isotope. of xenon. Right? This value up here will be, let's see, 2 and 142. Oops, sorry. Can't add. 12, 13, 132 is an isotope of xenon. Now, if you look at the atomic weight or the molar mass in the periodic table, it's 131.293. So 131.293. So what other isotopes could there be? We've identified 132, right? If you go higher than that, then you're never going to average this number. You need to go lower. So probably the other isotope that is most abundant would be something on the order of 131. Most of the elements have two major isotopes. One is more abundant than the other. And you can usually deduce them from the molar mass that's contained in the periodic table. All right, that was 10. Let's see. I'm going to skip down to 12. Here we go. So we've got this element, SC, with a 21 and a 45. And my first question is that even possible? So you look up whatever SC is. Do you remember what SC is? Let's see. Yeah, I had to memorize that one. A scandium. Scandium. We look on our periodic table. Yep, it has 21 protons. That's true. And 45. Yeah, based on its molar mass, that's a valid isotope. So then the question is, how many neutrons are there? Well, we know that that's the number of protons, and that's the number of protons plus neutrons. So we just need to subtract those two, right? 24 neutrons. That's 12. Let's see. I'm going to do 13, 14, and 15. Let's see if I can get them all on the same page. Yep, there they go. 13. Which of the following is a noble gas? So you just need to know where the noble gases are in the periodic table. Right? They're on the very far right column. And then just look for the one that matches. And I see the answer there. The only one there that's a noble gas is argon. I'm going to have to get another marker. Let me see. This one might work. How about 14? The chemical formula Al2O3 indicates what? Al2O3. Well, first of all, what elements do we have there? Oxygen, of course, and aluminum. All right. So what is indicated? 3 atoms of aluminum? No, I think there are 2 atoms of aluminum here, right? So it can't be A. 6 atoms of each element. Nope, sorry. 2 of this one and 3 of that one. 2 atoms of aluminum, 3 of oxygen. We got our answer, C. And 15. Si is the symbol for what? Well, that's one of the easier ones. It's silicon. Right? Silicon. Can you find it in the periodic table? Well, sure. It's in carbon's group. Right here. Right below carbon. I had a professor one time, I think it was a course in cell physiology. And he proposed, we had to write a paper. I don't know, I think it was a term paper, but it was a thesis of some kind. And he gave us the question or the statement. On such and such a planet, instead of carbon-based life form, there were silicon-based life forms. Is that possible? And explain your reasoning. So silicon's in the same family as carbon, so it'll have similar chemical characteristics, except they won't be exactly the same. So I went through it and made up my story, and that was it. And then not too long after that, I saw an episode of Star Trek. This was back in the 60s. Actually, no, it was in the 70s. It was a rerun. And they went to this planet, and there was a silicon-based life form that was burrowing holes through the rock. It was based upon silicon. Okay.
Did you say it was possible?
Well, that's science fiction. Theoretically, yeah. We don't know of any examples of silicon-based life forms, but it does have similar characteristics to carbon. They're not exactly the same. In fact, silicon is a much, much heavier element, so it might present problems there. It's not heavier and it's bigger. So if you had silicon-based life forms, the cells probably would have to be bigger. And then we know from the oxides of carbon is a gas. Oxides of silicon are solid, like sand, silicon dioxide versus carbon dioxide. So we get into discussions of whether the phase would even work in a cellular environment. Okay. And purple doesn't want to come off too easy. About what's next? Skip 16, 17. Let's see, 16, 17. Here we go. How many of the following did Dalton not discuss in his atomic theory? Okay. So you remember Dalton's atomic theory, what he said. He said that, and he was trying to explain why the chemical laws that had been developed up to that point were actually true. Well, the laws were true, but he wanted to explain why they were true. Right? We have the conservation of mass in a chemical reaction. We have the law of, these are the laws. We have the law of definite proportions. And then we have the law of, sometimes this is called constant proportions. And then we have the law of multiple proportions. Right? Conservation of mass was Lavoisier, and he said that during a chemical reaction, matter is not destroyed or created. In other words, the reactants are the same mass as the products. Definite proportions is that no matter where the compound comes from, the proportions of elements to one another by mass is the same. So we could purify seawater and get pure water, and the proportion of hydrogen to oxygen would be exactly the same as it is if we collected some of the outgas from the space shuttle engine, which is hydrogen and oxygen combined to make water. Be the same proportion. And this was Lavoisier. this was Proust. And multiple proportions was Dalton. He just says that in a series of compounds between two elements, you can have different proportions of those, and they would be established by this law. But if you had a series of them and you had the ratio to one of them, then the masses of the other element in this series would be whole number multiples. And Dalton was trying to explain that with his atomic theory. So he said, all matter is made of atoms. Borrowed that from the ancient Greeks. But the difference is, he said, elements are the same atoms. And then different elements are different atoms. And then he said, during a chemical reaction, we just rearrange the atoms. That explained conservation of mass. So if you have the same number of atoms on the reactant side as you do on the product side of the same types of elements, then you have the same mass. Okay, so what was not covered in this law? Isotopes. Dalton knew nothing about isotopes. He said all of these atoms are the same. Elements have the same atoms, and all the atoms of a single element are identical. They may be chemically reactive the same way, but they're not identical, because now we know about isotopes. Did he talk about ions? No. Had nothing to say about ions. How about protons? That's good. Dalton was before we knew that the atom was constructed of subatomic particles. He only saw atoms as black balls. They were different black balls from one to the other, but he didn't know what they were made of. Electrons? Nope. Neutrons? Nope. So how many of the following did Dalton not discuss in his atomic theory? All of them. All 5 of these were not touched by Dalton's theory. Okay, that was 17. How about 20? See if I can page down to 20. Yeah, chopped it off. Okay, 20. And that was starting to poop out on me too. Let me dig into my stash.
Is there a focus button that can be clicked to view the screen anymore? It went a little blurry out of, like on the from the camera side.
Okay, hold on a second. I think I may know what's wrong. Let me check it. No, it's not on autofocus. Maybe it changed exposure. And I don't have that on automatic. Well, white balance I have on automatic, but the others are, okay. It could have had something to do with the bandwidth going wonky on us for a second. Is it stable now?
Yeah, that's a little better.
Okay. 20. Think 20. Yeah, 20. The number of neutrons in Be. What is Be? Be is beryllium. So you just need to look up beryllium. let's see, it has, bring this over here with me. Beryllium is 4 protons. And if you look at the periodic table, you'll see that it's has an atomic weight, or a molar mass, we call it, 9.01. So a molar mass of 9.01 means what? Well, if atomic weight or molar mass in the periodic table is a weighted average of the available isotopes, then most of them are going to be 9 equals that mass number. So I would go with 9 here, which means you have 5 neutrons. Okay, that's how you deduce that one. The number of neutrons in beryllium, well, and you look at the best answer. In a multiple choice test, go with the best answer. Now, there may be, and probably is, a very small amount of beryllium with a mass number of 10. That's why it's a little bit higher than 9, but it's not due to very much of the 10. 9 is the vast majority of isotopes for beryllium. So the best answer is E. The second best answer would be A. Let's see, I think 21 is on the hit parade. Yep. Which of the following is a non-metal? Okay, so now you have to know how the periodic table is subdivided into metals, non-metals, and where that division occurs. Right. So you start at beryllium, and you go, boron, you go under boron, between boron and aluminum. And then you stair step down between aluminum and silicon, and then over between germanium and arsenic, and then over between antimony and tellurium. So you look at these choices and you say, okay, which is a non-metal? Right? It looks like carbon's a non-metal. Right? And if you're adept at multiple choice type tests questions, if you have no other of those weird selections like 2 of the above, none of the above, all the above, and that type of thing, then you can just work your way down, and when you find the right answer, you're done. And carbon is a non-metal. If we look at the others, cerium, cesium, calcium, copper, they're all over in the metals region. In fact, most of the elements in the periodic table are metals. Okay.
Now, if
Let's
the
see.
neutrons like ended up being like, say it was just like 4.4 when you had the answer, and your option choices were like 4, 5, and none of the above, would you want us to click 4?
For beryllium?
No, just like this is like a hypothetical. Like the answer is 4.4, but your options are 4, 5, and none of the above.
For the number of neutrons?
Yeah.
It would have to be a whole number.
So would you want us to round down to 4, or would you want us to click that like none of them are exactly the?
Okay, if you're starting off with that fractional molar mass, then what you would do is say which one is the most abundant. If it's 4.4, most of them are probably 4. Most of the isotopes probably have 4. And then since it's greater than 4, you might have a small number of 5s. So you go with 4 as the mass number.
Okay.
Okay. You should never have to round. By the time you get to that point, there's no rounding to be done because you can only have whole numbers of protons and whole numbers of neutrons. The reason you get a fractional molar mass is because of the weighted average calculation that you do. Okay, you remember that when we worked it with carbon? We had carbon 12, carbon 13 at relative abundances. And then we did the calculation for the average molar mass for carbon it works out to about 12.01. Right? But there are no isotopes of carbon that will have 12.01 as their the A number. Okay, 21, let's see, about 23. Well, let's scroll just a hair. There we go. How about the symbol for Mercury? Mercury, just have to memorize that one. Mercury is Hg. And it actually stands for Hydrogen, which was a reference to the use of mercury in experiments where water was a product. So we're creating water. Now, I don't think we do those experiments anymore, but alchemists used to do them all the time. How about 24? The symbol N stands for, that one should be easy. N stands for nitrogen. Well, can't say any more about that. It just is. N equals nitrogen. Except, what form do we find nitrogen at room temperature and 1 atmosphere pressure? It's always diatomic. Like hydrogen's diatomic, nitrogen, oxygen's diatomic. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. They're all diatomic. So if you run across a word problem that says you're going to react nitrogen with hydrogen, then when you write out the chemical equation, you better put it down as H2 and N2. We haven't got to that yet. We're balancing equations. I don't think we have we? No, we just memorized elements and wrote compounds. Okay, 26. Choose the pair in which the components have the same charge. Okay. Hydrogen atom and an electron. Do they have the same charge? Hydrogen atom and electron. Well, no, this one's neutral. Right? That's not the same charge. How about this one? An electron and a neutron. Well, no, not the same. How about a neutron and a hydrogen atom? Yep, same charge. This one's neutral because it has no charge to start with. This one's neutral because it's got 1 proton and 1 electron. And they cancel each other. So we're actually done. A proton and a hydrogen atom, nope, plus and a 0. And a proton and a neutron, nope, plus and a 0. So C is the answer to 26. How about, let's see, skip 28. Number of protons in the nucleus of an atom is called what? That's just definition. The number of protons is the atomic number. Right? Did we always know that the atomic number was number of protons? No. Not until Henry Moseley. When Henry Moseley found the atomic number, he was doing it based upon a formula. And the atomic number was just a whole number he could stick in that formula, and it changed for every element, and it was a whole number every time. That would give him the exact X-ray wavelength that he was receiving from that excited element. So it wasn't until later that we made the correlation between atomic numbers from Henry Moseley's experiments and the jump to numbers of protons. Okay, 29, I'm gonna have to scroll this one. Okay, 29. Which atomic particle determines the chemical behavior of an atom? And we were talking about how do you know a chemical reaction has occurred? Well, there are macroscopic indicators like evolution of gas. Maybe some of them give off light, some of them even make a sound. But what causes that? What causes the chemical reaction? When two atoms approach each other, what do they see first? Electrons. So the electron is responsible for the chemical behavior of an atom. How many of them does it have in its outermost region? I think we define those as valence electrons. How many does it have? Determines how it will react with other elements. How about 30? What's the most abundant element on Earth? 30. Okay. The most abundant element on Earth is the same that's the most abundant in our bodies, oxygen. On Earth, the atmosphere has 21% by volume oxygen. So the atmosphere is oxygen. Actually, the most abundant in the atmosphere is nitrogen. But we have substantial amount of oxygen in the atmosphere. How about oceans? Right? The Earth is covered, 3/4 of the Earth is covered with water. And that's H2O. Right? So there's your oxygen for that. And in the crust, most of the elements in the crust are combined with other elements. And the vast majority of those combinations are with oxygen. Okay? So that's why oxygen is the most abundant element on Earth from the crust up. Once you get down into the mantle and the core, you start picking up more silicon, and then in the core you get nickel and iron. Right, so we're just talking about the crust out. Okay, how about 31? I have to scroll that one. And let's see. Well, I can't get them both on there. 31, I know I'm going to need 33. Let's see, why do I have that one with a box around it? I don't know. How about 31? An atom with 15 protons and 16 15 protons and 16 neutrons would be 31. Okay, what is that? What element is that? Well, we just look in the periodic table. Right? Look for atomic number 15. And I think it is phosphorus. Okay. How about 33 is the next one? Thirty-three. And a certain isotope has a charge of 2 plus. It contains 37 electrons, okay, and 73 neutrons. Okay, what's the mass number for this element? What do we need to do? We've got the neutrons, we need the protons. How many protons? So we need to do a little detective work. 37 electrons, but it's got a 2 plus charge, which means what? It means it has 2 more protons than electrons, right? That's why it's 2 plus, because you have an excess of positive charge. So it actually has 39 protons. Right, now we know 39. And we add those two together. 112. So the mass number on this isotope is 112. Let's see, 33. Let's skip to 37. There we go. 37. How many phosphorus atoms are represented by one formula unit of cobalt-2 phosphate? And we were nice. We actually gave you the formula for cobalt-2 phosphate. Okay. How many phosphorus atoms are there? Well, you've got a polyatomic here, but you have 2 of them. You have 2 phosphorus atoms. Right? That's why you have 2 and not just 1. $37, $39. 39. Uh-oh. Must have accidentally bumped the key. How many atoms are represented by one formula unit of aluminum chromate? So this is how many total atoms are represented by aluminum chromate. Right? And we know based upon this parentheses that that's a polyatomic ion. But how many atoms are there? Well, you got 2 here. You got 3 chromium, and you have 12 oxygens. So we're talking about 17 atoms in that formula. All right. Let's see. About 40. Yep, we got it all on there. Okay. Which of the following statements are true? All right, let's look at our available answers. Roman numeral 2 only, 2 and 4, 1, 2 and 4, 1 and 3. All the above are true. What that means is you've got to look at every one of them. So let's look at Roman numeral 1. Is that true? Models are always wrong unless they are proved by a theory. Okay, that's kind of cryptic. But what it means is, actually, it's It's working under a false assumption. Theories are models are derived from theories. So you can't ever say that a model is wrong. It just, it either supports the theory or it doesn't support the theory. And you change it if necessary. It's never proved by the theory. Model is a supporting actor for theories. So 1 is false. How about 2? Elements such as lead are made of tiny particles that mostly consist of open space. Yeah, that's true. Most of an atom is empty space because most of the mass is right there in the nucleus. And then the electrons are way out here taking up a lot of space, but they've got relatively little mass. They're mostly open space. So that one is true. How about 3? The air you breathe is an example of a heterogeneous mixture. Is that true? No. The air you breathe is a solution. It's a homogeneous mixture. Right? So this one's false. Now you could argue, we're talking about purified air. If you have air with dust particles in it, or even water vapor, like in a rainstorm perhaps, then you could make an argument for a heterogeneous mixture. But what we're talking about here is a mixture of the gases that make up air. And that means it's a homogeneous mixture. 4, because ammonia always contains the same relative number of atoms, it will always contain 4.6 grams of nitrogen for every 1 gram of hydrogen. So they've got the formula there, ammonia. Right? And that's true because it has the same relative number of atoms. That's true. 1 nitrogen, 3 hydrogens. But how are their masses related? Well, what's the mass of nitrogen? It's 14.01. And 3 hydrogens would be 3 times 1.01. So 3.03 relative masses. Okay, so for every 1 gram of hydrogen, if we divide 3.03 into 1401, is that 4.6? Let's see. 4.6 times that. That's 18. That's 1, 18, and then 12, 1, and then 12. So 8, 3, 9, 3, 1. That's not right. I did that wrong, didn't I? Let me try that again. All right. So 3 goes into this one about 4 times. So that's 12. Well, that's 9. 1 minus 8. 1. So 303 into 8. 3 into 18 is 6. So it's about 4.6. Yeah, that's right. So for every 1 gram of hydrogen, you got 4.6 grams of nitrogen. 4 is true. So 2 and 4 are the answers. 2 and 4 is B. So what was I doing here? I was ratioing the mass of hydrogen to the mass of nitrogen in that molecule. We can tell that from the periodic table. All you have to do is look at the atomic mass in the periodic table for each one. And if you got 3 of them, like hydrogen, you just multiply it by 3. And hydrogen, I always round off the atomic mass in here to 2 decimal places. Right? So even if it has 5 or 6 decimal places, that's too much to deal with at this level. all we need is 2 decimal places, and the calculations work out just fine. How about 42? Which pair have approximately the same mass? Okay, proton and a neutron. That's true. Did we find the answer? Well, let's see. Yeah. Well, an electron and a proton are not the same. Proton's about 1,837 times or 1,835 times heavier than an electron. Hydrogen atom and a deuterium atom, they're not the same mass. Why? Deuterium has a neutron in it. And hydrogen, here they're talking about protium, has no neutrons in it. A neutron and an electron, no, they're different masses. Hydrogen atom and a tritium atom, oh, they're different too. Tritium has 2 neutrons in it. Okay, so the only one that fits is a proton and a neutron. They're about the same mass. That's why we say approximately. They're not exactly the same mass.
I have a question from off the last test.
Okay.
So when we're working with sig figs, if we have like an addition problem, like we did on the last one,
Yeah.
so the answer ended up being like 100, but really the answer was 100.00. Do we always keep the decimals?
Give me exact value. Do you have the numbers that we added together?
No, but hold on, I can just get like 2 that equal. So say like one's 52.36
Okay.
and the other one's 47.64.
Okay. Add those together. And what was the question? How many significant figures?
Yeah, or at the sum of this.
Okay. You line up the decimals. Both of them have 2 decimal places, so you can keep everything to the left of that line. 0, 0, 0. So you have 5 significant figures in the answer.
Okay, because when I don't know why, I just plugged it into like my calculator and I was like 100 and I was like 1, well 2. I was like, what's my answer? And I went with it.
Yeah, right. Your calculator is good at doing some things, but it doesn't know significant figures. In that respect, calculators are stupid. They're not built.
Yeah, well.
They don't have the built-in mechanism for giving you the right number of significant figures. You have to know that yourself.
Okay, so we always just keep it like the full number when we add 2 numbers together for sig figs.
Now, always is a bad word. You keep the least number of decimal places.
Right,
So,
but like in that case, we would always keep the 0, 0 on the end.
yes.
Okay.
If you had, say, a 1 out here, but that was it, like that, you would round that off to 100.00. Still 5 significant figures.
Okay.
Okay, let's see. 43, I'm going to scroll out a little bit. How many nitrogen atoms are in this formula? Right? Aluminum nitrate. First of all, is that written correctly? Oops. Nitrite, excuse me. 2. So if you look in your list of polyatomics, you'll find this NO2 has a -1 charge. And aluminum always has a 3+ charge. So yeah, 3 times 1- is 3- and 3+. So they balance. That's good. Now the question is, how many nitrogen atoms are there? You have 3 nitrogens in this molecule because you have 3 nitrite polyatomics and only 1 nitrogen per polyatomic. So the answer is E. And 3 nitrogens. Let's see. Why I marked that one out? So I did it for a reason. Let's skip down to 48. Oops. I have to scroll again. How many protons are in the atom? Carbon. Okay, you just need to know the atomic number, right? So you look it up. Turns out the atomic number of carbon is 6. Right? If you know 6, you know it's carbon. If you know it's C, you know it has 6 protons. I mean, they're joined at the hip. How about, oh, I'm going to skip some more. 51. Yeah, we'll scroll that one too. Okay, the symbol SN is what? That's one of those Latin ones. Right? SN stands for 10. This is Latin for stannum. 55. There we go. So, how many protons, electrons, and neutrons are respectively does this ion have? So we have scandium, there again, it's given us 45 as the mass number and a 2+ charge. So in order to do the protons, you got to look it up. Right? Look for scandium in your periodic table, and it has 21 atomic number. Okay. So it wants protons, electrons, and neutrons. Protons, electrons, neutrons. Protons, 21. Neutrons, 24. Right? Subtract 21 from 45. And how many electrons does it have? Well, it's missing 2 electrons, isn't it? That gives it an excess of 2 pluses. So it should be 19. 19 electrons because it's missing 2. So the answer is 21, 19, 24. Let's see, 55. Let's skip down. We're starting to skip more of them now because they're repetitive. 61. And scroll. There we go. 61. The average mass of a boron atom is 10.81. Notice the average mass. We're talking about the atomic mass. 10.81. If you look in the periodic table, let's see, boron. Yep, 10.81. So the molar mass of boron is 10.81. Okay? Assuming you were able to isolate one boron atom, right? That'd be a tall feat, but it has been done. The chance that you would randomly get one with a mass of 10.81 is what? What's the probability of finding an atom with that mass? It's 0%. You will never find one with that mass. It's a weighted average of a large collection of boron atoms. I guess you could call that a trick question, but it just, what it's trying to do is find out if you understand the nature of average mass. average atomic mass, you will never find an atom with that mass. 61, let's go to 65. There we go. Which of the following elements is most similar to chlorine? When we say most similar, what are we saying? Saying it's in that family. It's in the same family as chlorine. Chlorine is a halogen. So you know where the halogens are located? They're the second column over from the right. And what other atoms or elements are in there with chlorine? Not helium, not mercury, it's not hydrogen, it's not sodium. There you go. Bromine is a halogen. That was 65. Skip to 70. How many protons, electrons, neutrons are found in this one? Okay, we know it's neutral, right? So the protons and electrons are going to be equal in number. We just need to find out how many that is. Phosphorus is 15. So protons will be 15. Electrons will be 15. Neutrons will be 16. 15, 15, 16. I think 71 is on my list too. 71. Which of the following contains the largest number of oxygen atoms? Okay, all you have to do is know how these things are represented. How many oxygen atoms are in that molecule? Water, right? You got 1 times 4, right? So that's the number of oxygen atoms in that one. How about this one? You only got 3 in that one because there's only 1 of them. How about this one? H2SO4. Got 4 of those. Okay. 3 CO2. So 2 of these times 3 is 6 oxygen atoms. And this one, aluminum nitrate, yep, is 9. So the largest number of oxygen atoms is E, aluminum nitrate. Is that a type 1, type 2, or type 3 compound? Based on the metal, non-metal? It's either a 1 or a 2. Aluminum is a fixed charge. It only has a 3+ charge, that's it. So it's a type 1 compound. That's why we call it aluminum nitrate. We're done. Okay. 72. Yes, 72. I don't think I can get 75 on there. Let's get 72. Okay. How many atoms of oxygen are in the formula unit of calcium dihydrogen phosphate? Okay, now you have to know how to write the compound from the name. Calcium dihydrogen phosphate. Calcium. Dihydrogen phosphate is a polyatomic ion. If you know what phosphate is, you just need 2 more hydrogens. Then you need to know what the charge is, right? And you've been given the list, so you don't have to memorize it. But if you want to do a little detective work, what's the charge on phosphate? 3-, right? What's the charge on hydrogens, protons? 2, right? So 2 pluses cancel that 3 minus down to 1 minus charge.
Okay, this is a 2 plus charge. This is a 1 minus. Okay. So you need 2 of those. Okay. You don't have to do that now. Okay, so that's the formula. And the question is, how many atoms of oxygen are there? Okay. And 4 times 2 is 8. That's why the answer is D. Okay, 72, 75, I think is the next one I have marked off. Yeah, 75. There it is. Which of the following statements is true? Okay. Answers 1, 2, 3 are all false. 1 and 2 are true. Okay, we got to look at every one of them. We got 3 of them here. Is this true? The number of protons in an element is the same for all neutral atoms of that element. Yeah. Proton is identity. If you know the number of protons, you know the element. So the number of protons in an element is the same for all neutral atoms. In fact, they don't even have to be neutral. The number of protons will always be the same for an element. So this one is true. How about Roman numeral 2? The number of electrons in an element is the same for all neutral atoms of that element. That's true. You balance the positive charge, number of protons, with a negative charge, number of electrons. So they have to be equal in number. This is true. How about 3? The number of neutrons in an element is the same for all neutral atoms of that element. Not necessarily. You have isotopes. So this one is false. So the answer is 1 and 2 only. Let's see. Only 1 and 2 are true. Let's see. Next one I have marked off. Okay, now we're getting into chapter 5. And I've got the whole first page. Okay. Let me scroll, pick up as many as I can. There we go. We get the first 3. 76. The correct formula for carbon monoxide. Carbon monoxide. What elements are you talking about here? Carbon and oxygen, right? So, is this the type 1, 2, or 3? They're both nonmetals. Type 3, which means all you have to do is say how many of them there are. There's 1 carbon, 1 oxygen, CO is the answer. Carbon monoxide. 77. Which of the following is a binary compound? Okay, this is one of those questions. Some questions are best answered in reverse. Which of the following is a binary compound? Well, first of all, which are compounds? A is a compound, B is a compound, C is a compound, D is not a compound. That's a diatomic element. E is a compound. So we can throw D out right now. It's not a compound. Then we need to look at binary. Which is a binary compound? Okay, binary compounds are composed of 2 different elements. And the only one that has 2 different elements in it is hydrogen sulfide. These are made from polyatomics. Polyatomic, polyatomic, polyatomic. So they follow the binary pattern, but they're not, technically speaking, binary compounds. This is a trinary. This is a 1, 2, 3 trinary. That's a trinary. So D is the answer to 77. C is the answer to 77.
78. No, we skipped 78.
Okay, that's fine.
79, I think, is next. Yes, 79.
The correct name of an aqueous solution. The correct name for an aqueous solution of this compound. HC2H3O2. Oh, and it's aqueous. So we put that compound in water. And what does it do? First giveaway. Starts with a hydrogen. There are other hydrogens in here, but it's only got one in front. That's an acid. In aqueous solution, it's an acid. Okay, so we need to use the acid naming convention. So first thing you do for naming acids is you look for oxygen. Does it have oxygen? Yep. That means you do not start the name with hydro. You look to this part of the molecule, the non-hydrogen part, and say, what is this? This is the acetate polyatomic ion. And we know that when we form an acid from an 8, it becomes an ic. Acetic followed by acid. So that's acetic acid right here. $79. I think 80's on the list too. Yep, 80. So what does this symbol represent? Well, first of all, it's formed from sodium, right? But it's been ionized. It's lost an electron. So it is a sodium ion. Not a sodium atom, sodium ion. And our convention says this is a sodium, actually a sodium cation, because it's a positive charge. $80, $81, yep, 81. The name for Hg2 2+. Okay, remember I made a point of this one when we were talking about the elements. Mercury, Hg, when it forms ions, the ion is always 2+ charge. But if it's a single Hg atom, that means it's a 2+ for that one atom. But if it's a double, it's a diatomic mercury, then the 2+ means it has to be divided between two hydrogens. So, I mean, two mercuries. So each of the mercuries is a 1+. So when we put that in a compound, it could either be a 1+ or a 2+. In this case, it's a 1+. Right? So it's a mercury 1 ion. All right. $81, let's see. What's next? Whoa, the whole next page. Let's see, 82. Yep, we got 82 in there. 82. What's the correct name of the compound that results from the most stable ion for sulfur? Sulfur. What is the most stable ion for sulfur? Well, let's see. What group is it in? It's in the chalcogens. It's with oxygen. And all of those are most stable at 2-. Okay. Most stable ion for sulfur, and the metal ion that contains 24 electrons. So if this has 24 electrons, okay, this is not a good question, because you have to assume that there's only one of these. If you assume that there's more than one of these, that changes the calculation. So we have to assume that there's one of them. If it has 24 electrons and it's a matching charge to that, that means the protons have to be 26. If we look up 26, it's iron. Iron 2 plus, sulfur 2 minus. And when we write the name, it's iron 2 sulfide.
Let's see, somebody sent me a message, I think. Let's see what it is. Oh, yeah, that's fine. It happens.
Okay, so that would be iron 2 sulfide, not sulfate. Sulfate has an oxygen in it. Sulfide is just the sulfur ion. '82, '83, the symbol for rubidium ion. First of all, you need to know what is the symbol for rubidium, right? It turns out it's Rb, the symbol for the rubidium ion. Then you look for where is rubidium in the periodic table. I mean, can we say that it has, do we know what the charge is? Well, let's see, rubidium is an alkali metal. It's in the first column, which means it's always a +1 charge. So there it is right there, Rb +1. '84. What's the correct formula for barium hydroxide? Okay. We know we got barium. Okay. Hydroxide. There's no element in the periodic table that's hydroxide. That's a polyatomic. So you look it up on your table. Hydroxide. It has a -1 charge. What's the charge on barium? Well, you find that barium comes from the alkaline earths. So everything in that family, that group, is a 2+ charge. So that means we need 2 of those. And that's why the answer is E. Okay? Let's see. 85, 6, and 7. So I'm going to scroll that one. Here we go. '85. The correct formula for lead 4 nitrate. All right. You know you have lead. And you know the charge. And it's combined with nitrate, which is a polyatomic ion. Look it up, with a -1 charge. So now you have to balance the charges. 4 pluses needs 4 minuses. There you go. PbNO3 taken 4 times. Right here. '86. The name for the acid, HNO2. HNO2. It comes right out and tells you that's an acid, right? So it doesn't say it's an aqueous solution, but it has to be. That's why we say it's an acid. So we use an acid naming convention. It's got an oxygen in it, so no hydro. So we look at this. What is that? That's the nitrite polyatomic ion. And in naming acids, ites become uses. Nitrous acid. Right here. '87. The correct formula for the ammonium ion. Right? Just look that one up. It's the only positively charged polyatomic ion in that list. That's it. Right there. 87, 88. Oops, gotta scroll. The name for this compound. AlOH3. Well, there's aluminum. But what's this one? Well, parentheses is a giveaway. That's a polyatomic ion, so you know to look it up. Aluminum hydroxide. Now, do we need to say what the charge is on aluminum? No, it's a fixed charge. Aluminum can only be 3+. How about hydroxide? Do we have to say how many? No, because it's always a -1. So if we know this was 3+ and that's -1, we can write this formula again, just 3 times this one. Right? We don't have to say how many it is. So aluminum 3 would be wrong, or aluminum trihydroxide is wrong. So it's this one, aluminum hydroxide. It's not redundant and it's unambiguous. You can go backwards and forwards easily with no mistakes using this information. '89, yes, '89. The correct name for an aqueous solution of HCN. HCN. Okay. Oh, it is aqueous. It doesn't say it's an acid, but it has a hydrogen here, and it's an aqueous solution, so we use an acid naming convention. There's no oxygen. So that means we start the name with hydro. Then we say, what is this? CN is the cyanide ion. And ides become X. So we say hydro cyanic acid. Right here. '89, '91, and '92. Which of the following is named correctly? 91. So we've got several choices, right? We work our way down. Once we find the answer, we're done. Because there are no wonky ones in the D's and E's, none of the above, all the above, so forth. So how about HCl? Right, that should be hydro. Hydrogen chloride is the non-aqueous version. Once we put it in water, right, then we say hydrochloric. Right? It's hydrogen chloride, ides become X, hydrochloric acid. That's wrong. HNO3, right, has an oxygen in it, so we don't start with hydro. But NO3 is nitrate, and H's become X. So we say nitric acid. That one's right. So we can stop. This one's not the ammonium acid. Ammonium phosphate, no, because that's not phosphate, that's phosphite. And this is sulfite. So it would be sulfurous acid if it were correct. So the answer is B. That's the only one in that list that's correct. Matching formula with name. And 92, yes. This substance, ClO3 minus, is best described as what? A polyatomic molecule? It's an ion, right? A polyatomic ion. That's chlorate. That's the chlorate ion. All right, 92. I think we're skipping 93. Yeah. We're going down to 95. I was going to scroll it. $95. The correct formula for nickel 3 phosphate. Well, let's see. Nickel 3 would be this, right? And phosphate would be this. What's the charge on phosphate? Look it up. 3 minus. So there it is. A 3 plus balances a 3 minus. NiPO4 is the correct formula. That couldn't be simpler. Right here. I think 97, yeah, and 98. So I'm going to scroll to get both of those on the screen. Okay, 97. Sodium chloride. 97. So we know we have sodium. Is that right? What's the formula? Yeah. Sodium. What's chloride? Well, we had chlorate before. That's chlorate. Chloride is one less oxygen. And it's a -1 against a +1. That's it. We got our answer. $98. Correct name for an aqueous solution of H2SO4. H2SO4, aqueous solution. What would it be if it were not aqueous? It would be hydrogen sulfate. But it has oxygen in it, so as an acid, it would be not hydro, but 8 becomes it. Sulfuric acid. So it should be right here, sulfuric acid. What would hydrosulfuric acid be? That's hydrosulfuric acid. $98. About, let's see, skip down to 101. Here we go. The formula for the compound formed from the polyatomic ions, ammonium and phosphate, is what? They're being nice to us. They're giving us the ammonium as a +1 charge, and phosphate as a 3 minus charge. So all you have to do is balance the charges. You need 3 of those. Remember, polyatomics act as a unit, so you have to use parentheses. And there's your answer. 103. I have to scroll that one. The correct name for an aqueous solution of HCl. Okay. No oxygens. If it were not dissolved in water, it would be a gas, hydrogen chloride. So since it's no oxygen, we say hydro. And then I has become X. So hydrochloric acid. Hydrochloric acid. (103). How about 105? PI3. I'll let that go for now. 105. PI3. The compound PI3 is named what? You look it up, you look up where are they located in the periodic table. Is this a type 1, type 2, or type 3? They're both nonmetals. So they're type 3 compound, and all you have to do is say how many there are. You never say mono for the first one. So this is phosphorus. Tri iodide. And that should be here. Phosphorus triiodide. That was 105. Yeah. Let's get down to 107. What's the name of PB4 plus? Well, it's an ion, and we need to say what the charge is. So this is lead 4 ion. And there it is right there. What's next? 111. Got a page? Yeah. 111. What's the formula for selenium trioxide? Selenium, is that correct? Can we use type 3 naming convention? You know it's type 3 because there's a tri in here, saying how many there are. Well, let's see. Selenium, yeah. Selenium is a chalcogen. Oxygen, sulfur, selenium. So selenium combined with oxygen there it is. Simple as that. Oh, and that was B, SeO3. Let's see, skip down to 115. Here we go. Which of the following compounds is not named as an acid? Well, let's see. Which ones start with hydrogen? Are they all aqueous? Yep, they're all aqueous. Okay, we met that condition. How about starting with a hydrogen? That one's a hydrogen, that one, that one, that one. This one doesn't start with a hydrogen. Okay, so it's not named as an acid. I wonder what would its name be? Aqueous ammonia. Actually, when ammonia dissolves in water, it transfers a proton over here. Makes that plus, that leaves an OH behind. So if I were going to name it, I would say aqueous ammonium hydroxide. Okay, 115, 117. What's the formula for gold 1 oxide? Gold is what? Aurum. AU. Gold, 1 charge. Oxygen is a 2- charge. So we need 2 golds. AU2O. Okay, let's skip down to 121. Here we go. 121. The carbonate ion has the formula CO3 2-. CO3 2-. Okay. What's the correct formula for sodium carbonate? Sodium has a +1 charge. So that means we need 2 pluses to balance the 2-. 2 of these with 1 each balances that. Na2, CO3. Here we go. All right. And let's see, skip some more down to 124.
Is the bonus due at midnight on Thursday, or is it due at midnight on Wednesday?
Same day as the exam,
Okay.
Thursday. Which of the following represents the hypochlorite ion? Remember when I showed you those families? ClO3- is chlorate. ClO2- is chlorite. ClO- is hypochlorite. So there's your hypochlorite ion right there. Which one goes up here? Because you can put another oxygen in there. This one is perchlorate. 124. Dead and gone. 124. 125. Let's see, that chopped off part of it. Okay. 125. What is the formula for calcium hydroxide? We know we have calcium, and we know we have hydroxide. So can we write it with that name? Right. That would be a metal and a non-metal, or a metal and a polyatomic. Same convention. Would be a type 1 or a type 2. So we look, where's calcium? Calcium is an alkaline earth. It's always +2. This one's always -1. So we need 2 of these. CaOH taken twice. Right here. 127. Yep, it's still on there. The name of HBRO, aqueous. Okay. With an oxygen, we know we don't start with hydrogen. So we need to know, what is this? That's the polyatomic ion that is similar to the hypochlorite. This is hypobromite. and ites become us's. So it's hypo, bromous, acid. There it is right there. Um, 28, 29. Here we go. 128. The name for the acid H2SO3. Don't start with hydro. So we need to know what is this. That's the sulfite ion. So this is yeah, they say it's an acid, so it's sulfurous acid. The 129, the correct name for P2O5. P2O5. Type 1, type 2, type 3. They're both nonmetals. Type 3. So we only need to say how many of each. Diphosphorus. Pentoxide. Notice I dropped the A out of there. Pentaoxide doesn't sound right. So by convention, we drop the A and keep the O. $129. Let's see, what's next? 132. Here we go. 132. The correct formula for silver iodide. Type 1, type 2, type 3. If you look, where's silver located? It's a metal and a non-metal. So it's either 1 or 2. Where's silver located? If you look in your periodic table, silver is a transition metal. But if you also look in that little square, silver's only got 1 charge. It's only +1 charge. Never anything else. And iodine is a halogen. So it's always that. So AgI is the formula for silver iodide. You don't have to say what the charge is. $133, I believe, is next. Nope. Nope, we skipped down to 140. Chopped it off. The correct formula for lead 2 sulfite. All right, so we know we have lead. We know what the charge on lead is. So this is a type 2 compound. Because if we look for lead, we find that it could be a +2 or a +4. And then we combine it with sulfite, SO3, 2-. So here it is right here. PbSO3 is the correct formula. Let's see, we'll skip some more. 142. The correct formula for the carbonate ion. So you should look that one up. It's in that list. Carbonate, CO3. How many charges? 2-. And 143, I need to scroll. Oh, we got some detective work coming. 143. compound contains an unknown ion, X. It has the formula XCl2. Okay. We're given that. Ion X contains 20 electrons. Okay. What's the identity of X? Okay. This is a -1 each, right? So it has a 2- total for the chlorine, the chloride. So that means this one has to be a 2+, because there's only one of them. Right. We know that we have 20 electrons, but we need an excess of 2 protons. 2 positive charges in excess would be 22. So now we go to our periodic table and we look up 22, which is Ti. With a 2+ charge. Titanium. There it is. Ti 2+. Let's see. 147. Can I page? Yep. There we go. 147. The name for NaHCO3. Now, to name this compound, I'm using the modern version. Right? I'll give you the trivial name in a minute. This is a polyatomic ion. How do I know? 1, 2, 3 elements, and one of them is an oxygen. So this, figure this one out. This is a polyatomic. What is it called? It's called hydrogen carbonate. And this is sodium. Now, is that correct? Let's see. Sodium. Yeah, we don't have to say what the charge on sodium is because it's an alkali metal. It's only Hec +1 charge. That's it. Nothing else. So sodium hydrogen carbonate is the name of this compound. Sodium hydrogen carbonate. Now the trivial name is bicarbonate. Bicarbonate. Bi is a grandfathered term, which means hydrogen. Or, yeah, it means, in this case, it means hydrogen. So sodium bicarbonate is what you'll still see on the packaging for baking soda, sodium bicarbonate. Let me see, where am I headed? 147, 148. The correct name for an aqueous solution of H2CO3. H2CO3. Right, so there's carbonate. And we don't say hydro. So H's become X. It's carbonic acid. Right? And if you like pop, you're drinking that stuff. That's where the carbonation in your soft drink comes from. It's carbonic acid. So that's, let's see, here it is, E, carbonic acid. $153. Here we go. What's the name for this one? NH4Br. Polyatomic ion, right there. So it's ammonium. We don't have to say what the charge is because polyatomic ions have a fixed charge. Every one of them. There's one positive and all the negatives. They can only have one charge possible for each of the named polyatomics. And then Br is bromide. So ammonium bromide is the name. Let's see, we ought to be getting close to the end. Last one. 155. Oops, let's scroll. The formula for the compound formed from ammonium and sulfate. Ammonium is what? NH4 with a +1 charge. And sulfate is another polyatomic, SO4 2-. So we need 2 of these positives. NH4 taken twice, SO4. Right here. Okay. And my watch says class is over. 11 o'clock. Any questions? Okay. I think I got a couple of dead soldiers here. I'll throw these out. Okay, so if you're going to take the exam online, you don't even have to show up for class on Thursday. If you're going to take it in person and you want a paper exam, I'll have the paper exam sitting near the computer by the window in a folder. It'll be identified just for this class. And take it, get started, and I'll be along about 9:30 or so. Okay. Otherwise, I won't see any of you on Thursday unless you come here in person. Any questions? Okay. We'll see you later.